Thanks very much to the organizers as well for organizing this very nice meeting and for allowing me to present some of our work here. So this is joint work with Xin Huang and Anders Szepessy, who are both of them at KTH in Stockholm as well, and Petr Plechac, who is in the University of Delaware. And as you see from the title, it mentions both the quantum mechanics and molecular dynamics. So that is sort of the overall goal, to try to link these concepts somehow, to see how related are they. So quantum mechanics and molecular dynamics is two ways to describe matter. So quantum mechanics is, as we've heard in the lecture by Professor Antoine, can be seen as an eigenvalue problem in a Hilbert space. So there is a Hamiltonian operator, and this phi here is called the wave function that sort of carries all the information about the state of the system. And E, the eigenvalue here, is the energy of the system. So that is one way to describe matter. And the other way is molecular dynamics, which is written here, which is basically the classical dynamics, so Newtonian mechanics. So X is the position of all the nuclei or particles in the system, and P is the momenta. And if we know how particles interact with each other, so we know this potential, say that Vjk is the potential between particles J and K, then we could integrate this. So this would correspond to molecular dynamics with constant energy, but one could also have some stochastic terms here to take care of system with a constant temperature, for instance. And then the question is, what should one do? Should one do the first or second here? And if one consider the Schrödinger equation, so if we have this Hamiltonian operator H hat, if it's given like this, then we have the Schrödinger equation, which you see it's a partial differential equation. We have the Laplacian with respect to the capital X coordinates, which is the nuclei with the small x particles. And then we have Coulomb interactions. We have Coulomb interactions here between nuclei and electrons, between electrons, and between the different nuclei. And it's very nice, this setting. It's good for mathematicians. In a way, it's completely clean. Everything is known here, sort of. The only problem is that, I mean, it's a linear operator here, for instance. So the theory is very well established for solutions to such problems. But it is suffering from this curse of dimensionality. So it's a PD in 3 times n plus m, if n plus m is the number of nuclei and the electrons. So for instance, for a water molecule, that would be a PD in dimension 39 or something like that. Maybe there are some degrees of freedom, some symmetries, one could decrease that somewhat, but still it's sort of, for even for very small systems, it's not easy to get the solution to this problem. So with quantum mechanics, there are many nice properties. So for instance, no unknown parameters. I chose coordinates such that now this Planck constant is equal to 1, but even if one have that, everything is known in sense of coordinates. And as I wrote here, maybe it's giving the exact answers in some sense, or is it exact? I don't know. It's in question mark, but it's at least it seems to give very accurate predictions about matter. But the big drawback is the complexity. Whereas molecular dynamics, that's one can do for much higher dimension. I mean, several hundreds of thousands, or I don't know, millions of particles. But the question is, I mean, how accurate is this? For instance, we had on the first slide the potential acting between particles. What is that potential? Do I know it? In general, maybe one would model using a pairwise interaction between different nuclei, but in reality, it's not working like that. I mean, you have several particles in the vicinity of each other, and they are sort of connected with molecules or with electrons that interact with several particles. So it's not just pairwise interactions between the nuclei. The one thing one can do then, in order to simplify life, if one want to think about quantum mechanics and sort of use that as a stepping board to do sort of reasonable molecular dynamic simulations, is the so-called Born-Oppenheimer approximation, where one approximates the Schrödinger or the solution to the quantum system with just molecular dynamics using the lowest eigenvalue of the electron over the electron coordinates. One has this sort of ground state over electrons. And we will do something similar to this, as you will see. So this will be the objective for us. And I will describe why do we want to compute this thing? What does it represent? So we want to compute this quantum mechanical, observable, this calligraphic T. So it involves these traces, and you see we have these things with hats on. These correspond to quantum mechanical observables. And why do we want to have the trace and so on? Okay, so let me begin by saying, what is this A hat T? So this would be the time evolution of a quantum mechanical observable in the so-called Heisenberg representation of quantum mechanics. And this corresponds to the time-dependent Schrödinger equation. So say that we have, here we have the time-dependent Schrödinger equation, and you see the solution at future time t can be given like this. So the solution operator would be e to the minus it square root of m h hat. So that means if we would like to compute the expectation of the operator a hat at some time t into the future, we have what's here on the left-hand side, and then using that phi t solves the Schrödinger equation, we see we can, I mean, by defining this a hat t as up here, we see this, I mean, it's the same thing here on the left and right-hand side. Oops, down here. So that is what this a hat t means. So we want to be able to talk about some time-dependent processes and compute these. Okay, and what? Yeah.
Sorry, very quick and maybe a stupid question. The a hat, would that be the a hat 0?
Yes, that is, yes,
Okay,
A hat 0.
thank you.
Yeah, that's a good question. Yeah, it's and trace. Why would we want to have this trace? So I put this quantum mechanical observable here again. This is what we're aiming at. So we see there is a trace here. So if we have a trace of an operator, we can take, if we have a basis, say we take all the basis vectors phi n of the space, then we could write the trace like in this equation here on the top. And here we have now the trace of something times e to the minus b h hat, so the Hamiltonian, which is giving us, when we take the trace, then that means taking e to the minus b hat times this phi n. So if we use the phi n as the basis given by the eigenfunctions of the Hamiltonian, this gives us sort of observables of a hat with these weights. So this is giving us the so-called Gibbs distribution of energies, which one have if one have a system that is in a heat bath. So I mean, if we have an isolated quantum system, it will retain its energy constant. But if we have a system that sits in a heat bath, so it's surrounded by particles around it, and it exchanges energy with the surrounding, then the energy in the system that we're interested in, that would be distributed as e to the minus energy divided by temperature. And 1 over temperature, this is what is denoted as beta here. So this is a way to, by using this trace, we can, with this operator, we can then get the Gibbs distribution corresponding to a system at a certain given temperature. Oops. And time-dependent things. For instance, if we would like to compute the diffusion constant, well, then we would need to compute something like this, squared deviations if we start with dynamics in some point x0 and go to time tau. Okay, if we would extend this square, we see we get something involving x tau times x0. So then quantum mechanically, we would like to have, say, operators from x hat tau, x hat 0. And as we will see soon, in fact, then one can approximate this thing that we had on this previous slide, this quantum mechanical observable, using molecular dynamics. We can approximate it with something that is much easier. So here is a new Hamiltonian, which is almost the same as we had before. Now there is no hat here. So P here is now the sort of classical momentum variable for the nuclei, and we still have the Laplacian with respect to the light electron particles. But in some sense, what we have done is we, instead of having to compute all these eigenfunctions of the Hamiltonian, full Hamiltonian operator, I should say, we now have instead this MD simulation. This is just computing integrals over the full state space. So this is R6n because we have three n coordinates for position and 3n coordinates for the momentum. So, and then we compute over these integrals over these. And now, as I wrote here, the trace, this is something else than what we had before. Now, this is just the trace that remains this is the partial trace now over only electron coordinates. But we will come back to that question. This is actually the main question that we will consider later on. I mean, how do we compute this trace in order to be able to use this molecular dynamics approximation? We will need to be able to handle that. Okay, and what is it that we need to compute? So I forgot to say that here, here you see we are integrating over initial condition Z0, and we have Z of t, which depends on Z0. So here is some classical dynamics, Hamiltonian system going from initial position to time zt. And this system, we also need sort of the trace of the electron variables to define. So this is driven by the so-called mean field Hamiltonian, which is the lowercase h here. So here we have the Hamiltonian system with this h, where this mean field Hamiltonian, again, this is the trace of over electron coordinates, which now depends parametrically on the heavy coordinates, capital Z. So the capital Z is capital X, capital P. So this is position and momenta of the nuclei. So for instance, if we have if we say the eigenvalues of the electron operators are lambda I, then this mean field operator H, it will be the kinetic energy, and this kind of sum over the lambda i's, which is the energies from eigenvalues of the electron operator. You see then, if beta is large, that is beta is large means temperature is low, well then that means that sort of it would be the ground state energy that is totally dominating. But if we have high temperatures, then one would really need to take not only the ground state into consideration, but several states as well. Okay, and then we have this result. I will give the reference in the end. So we can bound this difference between the quantum mechanical observable and the molecular dynamics observable. So if there is no, if we have time independent observables, then it is depending on 1 over m. And I mean, we did the analysis as well for with an approximation that, or we assume that the electron operator can be, we have the case where that is represented by a finite dimensional matrix. I mean, for to do the analysis more less complicated. But anyway, then we can see that this difference is of the order 1 over the mass, where m is the quotient between mass of nuclei and the mass of electrons. So that means at least 1 over 2000. And then if you have time dependence, we also have these terms here. And let me just indicate, I will not show the proof of this result, but I just want to indicate how this reasoning, to the linking between the quantum and the molecular dynamics goes. So for that, we need to define sort of what do we mean by quantum mechanical operators and the corresponding molecular dynamics operators. So here you see, when I define this molecular dynamics observable, we have operators A and B. Before we had quantum mechanical operators A hat, B hat. And the relationship goes via this relation. This is the so-called Veil quantization. So if one have classical operator A, which is called the symbol of the quantum mechanical operator A hat, they are related as follows. So if we, for instance, so you see, we have this integral here over this p variable, the momentum variable. So say, for instance, we have a observable that only depends on x. Well, that means we don't have a p here. So you see, what we do then is integrate this exponential function over p. So this is what we have is a Fourier transform of delta, direct delta, for x equal to y. So that gives us a direct delta, x equal to y times phi y. So what we get out is a of x times phi of x. So an observable that only depends on x is the same as the classical, I mean, acting as a multiplication. And if we would have, say, this kinetic energy, p squared, well, then we see we have a p squared times this exponential. So it's a Fourier transform of a direct delta with two derivatives. So we get, I mean, the Laplace operator. So I mean, it is the correct thing, sort of. I mean, we know that this classical kinetic energy corresponds to the Laplace operator for the Schrödinger equation, and the potential just acts as multiplication. And then this Veil quantization sort of interpolates between all other operators as well. And you see this thing here, we could write as an L2 kernel. So we could say that a hat phi of x is some, I didn't write it out and name it, a kernel, say kx comma y. So then we have this integral here, kxy phi y dy. Maybe I should have a hat phi point x is equal to integral kx y phi y. Oops. Poor handwriting. Phi y dy. And then a way to get this trace, I mean, the trace is defined like this. This is a very complicated object here, clearly. I mean, just to use this operator, I mean, this is, if we are in high dimension and we have a partial differential operator, this is not easy. And I mean, then we would like to say find, I mean, you compute this 1 million times or something to approximate this up. But the trace of such an operator could also, I mean, if we have a kernel here, this is equal to the integral kxx dx. Like if we have a matrix, one way to compute the trace is just to sum the diagonal elements. This is the corresponding thing. So that is, of course, much easier. If we use that, we have this Veil representation. This is this L2 kernel representation. Well, then what we do then is we integrate this L2 kernel, sort of putting x equal to y. Well, that means this exponential function disappears, and we just have a of x comma p. When we integrate over both x and p, since also this L2 kernel in itself has this integral over p. So that this gives us this correspondence, right? We have the difficult quantum thing here, the trace over a hat, which has this much simpler representation as an integral. This is the sort of classical object here. That is something much, much easier to compute. That is for just one operator A hat. This here we have this correspondence, quantum and classical mechanics. It's equality everywhere. And if the same thing also holds for product of two observables, A hat, B hat. That's also this integral. Unfortunately, it does not hold for three observables. Then one don't have this nice formulation. And I mean, so one have to put in some work then to if we would like to represent this quantum mechanical observable with time, this time evolution by molecular dynamics. And even if one don't have time dependence here, there is still some work that has to be done because of some technical things. So okay, so but that gives us this correspondence anyway. So we want to be able to compute this molecular dynamics. So, and I cheated a little bit here. So now what I wrote here, we have used that these operators are only depending on nuclei coordinates. So for instance, if we have the diffusion, we want to compute the diffusion constant. We only think about the diffusion, how the nuclei diffuse. The electrons, they kind of move along. So operators that only depend on such. And then this trace is over the nuclei coordinates. So that gives us this integral over nuclei space. But the Hamiltonian, it depends on electron coordinates. So that's why in the we still have this trace over electron coordinates with the Hamiltonian. So that is then the main question after this sort of long introduction. How do we compute this? Now we can use this molecular dynamics observable to compute or approximate what we want to have, the quantum mechanics. But still, we need to be able to compute this trace here. We need to be able to compute this mean field Hamiltonian. So it is this trace we have in the bottom here, where we now have the Hamiltonian as before. It's classical in this p variable, but still we have the trace over the PD operator here. So the Laplacian over electron coordinates. So one thing to note is that if we can compute this so-called partition function, the normalizing, I mean, we have it here as well in the normalization, the trace of e to the minus b beta h e. So h e. This is the electron part of the Hamiltonian. So this part here. If we have that, then in fact, in some sense, we have the mean field Hamiltonian as well. I mean, it's defined like this, which we see we can get it by taking the derivative with respect to this beta parameter of the logarithm of this partition function. So how do we compute that thing? So we can observe that this e to the minus beta h e, this is the solution operator of the parabolic PDE. If we would take the time derivative of some function u and h e times that u, that's a parabolic differential equation. So in fact, we could relate this solution operator to stochastic differential equations using the Feynman-Katz theorem. So by the Feynman-Katz, the solution operator of that parabolic PD is related to this expected value here. So here, this x, the small x of t, is just a translated Wiener process. And why is that? Well, that is because this Hamiltonian, it has the differential part is just the Laplacian here. So the corresponding stochastic differential equation, one could write it as dx equal to dw. So the solution is actually equal to the Wiener process, but translated with the initial position. So that gives us this possibility to sort of handle this. And again, the trace, it's like over here, that would correspond to having start and end positions in the same position. X end time beta equal to x0. So we have an integral over x0 where we set x beta and x0 equal to equal. And this is the case if we would treat the electrons as distinguishable particles. So this is not the truth. But say we would think about the electrons as distinguishable particles, then this trace could be computed like this, which means that we can compute it using Brownian bridges. So it says, it's stated here, we have two options how to compute this thing here. Either we sample directly over these initial positions x0 and compute this expected value. We have to discretize the paths and so on, but compute this expected value for each x0. Or we do another thing, which is called a Schrotter splitting of this operator. So then we can see that this trace, we can compute it if we take, we do a discretization of the integral. So we have a sum, v times delta t, where x would be then this, the value of the Brownian path. And then we could also take, if we remove the expected value, and we know that, the density of this Wiener process, the delta W, if you so wish, that is completely known. It's this Gaussian. So another way would be to compute this integral over the full space, the discretized path. So this is called the so-called ring polymer. So it's not at all a polymer, but it's a ring in the sense that we have these periodic boundary conditions. We go from x0 and we go back to x0. So if we discretize that, it's a little bit like having particles in a polymer, something that is round, say. So one have these two ways to attack that problem. Okay, so this is just it's not the truth what I've said so far. With the distinguishable particles. In fact, the electrons are indistinguishable, and the wave function needs to be anti-symmetric over the electron coordinates. And that leads to the following, that the trace that we are after must be computed as follows. It's not just one sort of Brownian bridge starting from x0 and going back to the same point x0. Instead, what we get is this sum over permutations. So you see here, we sum over sigmas in S. S is the set of all permutation of these electron coordinates. And we take the signature of that. So the permutation, if you flip two coordinates, that gives you a minus sign. And then if you flip two other ones, or for every flip, you change the sign. So that becomes much more difficult. So to see this, one could use the representation of an antisymmetric wave function as this thing here. And one could mention as well that for bosons, their wave functions are symmetric with respect to coordinate changes. So then one have the same thing, but the signature is removed. But again, we have to compute sums over permutations. So we start in x naught and end up in x beta. And the x beta must be some permutation of this x naught. Okay, so again, we could use Brownian bridges to compute this, or rather sort of translating Brownian bridges. So if we are to go from x naught to x beta, which x beta is equal to this permuted x naught, we could do it like this. We have the linear interpolant between x naught and x naught sigma, and we add a Brownian bridge. So that would be the sort of Wiener process connecting these 2 points. So that would give us then this trace here as follows. And yeah, so, and again, it's the same for bosons, but then we don't have the signature. And this has a big problem here, very big problem, which is the so-called sign problem. So for bosons, we don't have the sign here. That means we only sum positive things. For electrons, or fermions, one has the sign, which means we have huge cancellations. So basically, I mean, we want to compute an integral. The integral is of order 1, it's positive, but there is a positive part and a negative part, and they almost cancel each other, especially if beta parameter is large. So I mean, that is going to be a big challenge. Say you have the positive mass 1,000,001 and the negative mass 1,000,000, and now you want to somehow, I mean, compute the entire integral. This is really a difficult problem. So if one take into, one would need to sort of try to use cancellations of the positive and negative parts in order to circumvent this. Okay, so two things here to address. One would like to attack this sign problem. It's a very difficult thing. We have tried to do that. There we have not, I mean, we have not succeeded. But I will tell you a little bit about this problem, how it sort of could attack it. And then we have an idea of how to overcome this complexity. I mean, we have to take the sum over all permutations, so n factorial. And there one can do something better, but it's approximate. And yeah, I'll come to that. So in dimension 1, then in fact, there is no sign problem in this sense. So here is a result from a PhD thesis by Dumas. And this seems to be sort of well known in physics community. So for dimension 1, you see this thing that we are computing, we want to take the sign over all permutations, which gives us something difficult. In fact, we can compute it without taking the signs. That is, taking the expected value of this exponential integral of exponential of the integral only for paths that do not cross. And how do one show this? So I won't go into details, so I prolong unnecessarily. So I don't want to go over the time. But in some sense, it's a mirroring argument. But one takes the expected value, conditioning on having some crossing of paths. So let me just give you a little bit of a picture. So if you have the starting positions and you have end positions, the theorem says that if so long as all these paths do not cross, they count towards what we have on the right hand side. They are counted. But if they cross, they are killed. And in fact, this one can show by some mirroring arguments. So if two paths happen to cross, say we have paths from here and here, and we condition on this fact that they will cross, then it's from the point that they have crossed, it's equally probable that one have the transition that they cross over to the other side, or that they sort of follow the same path but go like this, sort of go back and don't have crossing, and I mean don't permute. So that leads to a big cancellation. All the expected value condition on having paths crossing will totally disappear. But this technique only works in dimension 1, unfortunately. And yeah, we have tried to one would like to have it for electrons in dimension 3 where they live, but that is difficult to achieve. But that would be great if one could achieve that. Then one would have this sort of correspondence really between quantum and molecular dynamics. But what we do, we propose the following algorithm that at least takes away this n factorial complexity with respect to all the permutations of the electrons using a determinant. So to begin with, if we assume that the potential is separable, so that the potential can be written as a sum of potentials such that electron k only feels the potential v tilde k. Well, then, in fact, this Hamiltonian, the electron Hamiltonian, can also be written as a sum of operators that's acting on each coordinate separately. So we can separate this operator. And if we then define a matrix WKL, so the entries of this matrix is the integral of this v tilde of this translated Brownian bridge that starts in the xk and then in xl. Then, in fact, we could write this partition function as the determinant of this matrix W, just by calculation, sort of using that the exponential of these v tildes here, when we sum them, they will become the total potential. And so that means in that case, if we have such a separable potential, then this trace is equal to this integral over determinants of these matrices. And determinant one can compute in O of n3, n cubed. If one use LU factorization, for instance, and do the determinant, that can be done in n cubed. And that seems quite particular. So if, for instance, if one would do this, the same thing for bosons, then one would have this same thing here, but without the signature. And that, I didn't know that before, it's called the permanent of a matrix. And that is not, I mean, that is still n cubed. It seems that the determinant is somehow very particular of a matrix operation. So in that sense, actually, the sort of the fermion case is easier than the boson case with respect to number of particles. But I mean, the bosons doesn't suffer from this curse of dimensionality. Okay, so this was an assumption of having a separable potential. In fact, it is not. I mean, the electron potential looks like this. I mean, the potential is a sum of Coulomb interactions. So we have interactions between the nuclei, we have nuclei electron, and then the thing that makes it don't work precisely is this interaction. We sum over all pairs of electrons. And again, if we consider one electron which sits in the position xk, again we could split this potential v, or I mean, yeah, the things in this potential v that depends on the electron coordinates as a sum of vk. But you see this part here, it's sort of centered around xk, but it's also involving all the other particles. So we cannot separate this particle-wise, which means that if we do the same thing as before, okay, then we should sum over the sigmas, but here we have a sum over k and k prime from xk to sigma k and xk prime to sigma k prime. So here is some operation of I mean, if we would say, call these indices k, l, m, n, it's like a fourth order tensor. And then we do some kind of operation here with all these permutations. That seems to be very difficult. I mean, we found this paper, they state the number of operations involving tensors. They state this, that most tensor problems are NP hard. These have, for instance, approximation by one order tensors or rank one tensors of when one have third order tensors and eigenvalue problems and so on for order 3 tensors, and the permanent, as I mentioned before. So it seems that is not so easy to compute this thing in low complexity. So what we do then, well, we do this approximation. We would like to use the determinant formulation because that has this n cubed complexity, which is much better than n factorial. So what we do is we sort of think about all the particles, all the electrons, except this one that sits in xk as some kind of mean field. So instead of having this term 1 over xk going to sigma k and xk prime going to sigma k prime, we take another permutation nu here, which we define as this here. So basically, for most of the other particles, we just let their path go from say, xk prime back to xk prime. So basically, it's some kind of mean field approximation here. All right, if we have, oops, doesn't matter. We can use yellow color. So if we have our particle k here that we consider, I mean, in some sense, then we would need to have, I mean, all of these other particles. Oops, maybe they are not going to the same place, but we have transitions between all these particles in some sense. So maybe then the interaction here with this particle and the others, I mean, we have in. Thank you. So that is what we do here. Then we have we use this permutations that so particles go just back to the where they came from. Except if we start if k prime would be equal to sigma k, well then we don't want to go back to the same position, because then we would end up in the same position at the end time. So we go. So what for two particles, this then becomes exact, and we have this as well. This approximation of this partition function, which we now can. I mean, this is a formula here for this new partitioning. So what we have here, when we sum over this j particle, is something that only depends on k and sigma k, which means that this whole thing can be formulated as a determinant. Okay, which gives us, as before, something that we can compute in order n cubed complexity. And it's exact if we have only, I mean, one permutation, and for low beta, the identity permutation and permutations involving just one switch will be the dominating one. So we can expect it to be accurate for small beta, in fact, because then, I mean, those are the permutations that sort of count. And it seems I mean, we don't have a theorem here for the accuracy of this, but our numerical tests indicate that, in fact, it seems to work with fairly good accuracy. So here are some numerical tests. So to begin with, if the potential is the following, we just have a quadratic potential. Well, then, in fact, this trace, it has an exact value. So we can use that as a reference. And moreover, it's also separable. So this determinant formulation should be exact, and we test it. Okay, so that seemed to confirm it is correct, this determinant. So here is the Monte Carlo simulation, and if the time discretization error is one make that small enough, it just continues. We see the sort of m/1/2 convergence rate. So that seems to, yeah, that is working as we know it should. if we have another potential that is not separable, so we can write it as a sum over potentials that only depend on the xk. Then we found the paper where they have this Thomas Dornheim has computed some reference values for this potential, which has also confining x2 potential, but as well Coulomb interactions. And lambda is just some factor to set, giving the strength between the two. So he has used lambda equals 1/2. So we tried the same thing. And then it seems, I mean, that this age ref is the values that he has obtained in his article, Thomas Dornheim. So this here is for n equal to 6, that is 6 electrons, and we have the values for different values of data. And here is the approximation we get if we use this determinant formulation. And it seems, I mean, it gets worse as we expect with larger beta, but still, to us this was quite surprising. At least, I mean, to begin with, we weren't sure that if it was exact or not. I mean, we had to really work to get. So Xin did a great job here with doing the simulation and having to wait a long time. But for beta large here and doing the simulation with enough many samples, one can see it is really. I mean, we don't get the exact value, but it's. I mean, it's at least to us that seemed more accurate than what one could hope for in some sense. And here is another case. This was for electrons living in 2 dimensions. Yeah, so again, the difference is not so large. This is even for 20 electrons here. And we also did, I mean, yeah, we wanted to check a little bit how, if we could trust these reference values. And I mean, they seem to be okay. When we do the full tensor approximation, or I mean, which is exact if we take, I mean, if we can reduce the statistical error and the time discretization error, we see we get accuracy that's comparable to, or I mean, the values correspond to the values in this reference. Okay, so here are I stated these references and the conclusion. We have this, we propose a method for this problem. It is giving the complexity O of n cubed instead of n factorial. And it seemed to be working accurately, but yeah, that remains to be shown rigorously. And still, this sign problem is, I mean, that is unsolved, and that would be fantastic if one could. Yes, we have tried, but so for instance, yeah, we have some analysis that, or there are results that say that if the beta parameter is not too large, then one have some, I mean, distribution of the number of switches that sort of play a role, which is not too large, and then somehow one can see in this sort of xk minus x sigma k, if one think about cycles that are longer than 2, if we take the marginal distribution with respect to all the other particles, it seems it doesn't change this thing too much. But yeah, but we don't have any sort of hard evidence now. Yeah, so how to deal with the beta large? Yes, that's, I think nobody really knows. Because of this sign problem, it's, I mean, so, yeah, where I should look now, but here one really have huge cancellations if the beta is large. So in some sense, for the 1D case, then one can see one can sort of, one can really cancel the negative and positive parts. Even then, it's in some sense, it's not solved for beta large, because what happens, so all the paths that cross, they are killed. They give 0 weight. So if we are in one dimension, I mean, if you have a large time interval, I mean, this is the time interval which is beta long. So clearly, if you have a large interval, then almost you will have crossing. But it's better anyway, because you don't have a cancellation then, at least. So it's not a sign problem, but it's still not easy.
Okay, one last question, because I see the next speaker is already waiting online.
Just not question, remark. Tensor community, they solve Coulomb, Hartree-Fock, Schrödinger potential very successfully. So I spent with them 5 years in previous life, and very often I heard these talks, and yeah, I just wanted to tell you, maybe you do not know, for example, people in Leipzig, Max Planck Institute.
Thank you.